Welcome to Foundational Elements of Electronics Prototyping. Sensors, actuators, and microprocessors. These components are building blocks of smart systems, enabling them to sense, compute, and act in response to their environment.
Sensors and actuators, they are inherent part of our daily life. We have multiple sensors in our day-to-day life, like in our home, we have now automations. Multiple sensors are there in the home, starting from lighting on and off, the room lights, illumination can go up and down, thermal, and all these, thermal control. So in those cases, when the information comes to the machines, so in this case, what could be the machine? Machine could be those sensors, which are conveying that information back to the control unit, which is used in our home automations. And what those control units are doing? Control units are conveying back that information to turn on the light, that is the action, or turn on the fan, or turn on the AC, that are the actions. So same kind of example we can take extended to the manufacturing setup. There also we have machines, we have operators, and machines have their own sensors, operators have their own sensors and actuators. So machine gathers the information from the environment for doing some action on the jobs or the objects what given to the machine. At the same time, operators also collect information from the environment through their biological sensors or the natural sensors, and they do take action on the environment. And this interaction plays a big role to getting something manufactured in the industry, or assembled, or tested, or repaired.
Now that we have explored sensors, actuators, and microprocessors, let's move on to the next level, signal processing and communication.
Sensors are basically transducer. Initially, they are designed in the lab with controlled environment. However, manufacturing industry or in real habitat areas are having very much harsh environment and wide variations, which need to be considered in sensor design to cater specific need in different scenario, but easily like a plug and play. That's why we are having smart sensor and intelligent sensor. As for example, small NTC thermistor to TC1047, which is a smart sensor with temperature to voltage controller having wide operating range with 3-pin VCC, ground and output. If we take another example of TC623, which is a dual trip temperature sensor, can be used by setting high and low limit with one control output pin to drive a fan or generating a trigger pulse. When we are talking about intelligent temperature systems, they will have sensing, processing and communication port, mainly IoT based. For example, thermostat based heating or cooling chamber using Wi-Fi temperature sensor. All these systems require ADC, online digital data processing and analysis before passing the result. ADC is advantageous for data analysis, lowering transmission noise, etc. We often need to use signal processing techniques to transform raw sensor data into meaningful information, like by filtering noise, amplifying signals or applying different analysis process. We ensure that data is accurate and usable for decision making or further processing. Digital data are of two types. One is temporal, which is related with the time, and another is spatial, which is related to the space. So spatial data deals with image. Image processing is done on image enhancement, image manipulation and feature extraction. Image manipulation is generally used to reflect ideas, whereas basic image enhancement with filtering and other processes are often used and even serve as a precursor in feature extraction.
Communication is backbone of interconnected systems. Protocols like I2C, SPI allow sensors and actuators to share data, ensuring seamless operation in complex applications like IoT and robotics. Consider a wearable health monitor. Sensors capture heart rate and motion data, signal processing cleans the data, and communication protocols transmit it to your smartphone. This integration demonstrates the real-world importance of these concepts.
With an understanding of signal processing and communication, we are now ready to explore applications with FPGAs and industrial communication. In our final video, we will delve into FPGAs and their applications in electronics. We will also explore how industrial communication protocols enable robust and reliable data exchange in advanced manufacturing systems. Field programmable gate arrays (FPGAs) are essential in smart manufacturing, enabling custom hardware design through programmable logic circuits. They support applications such as real-time data processing, automation control, and system optimization, enhancing efficiency and precision in manufacturing processes. Industrial communication is vital across diverse sectors, enabling real-time data sharing among machines, sensors, and control panels and systems. Protocols like Modbus and OPC-UA enables reliable, scalable connectivity, improving automation and efficiency in manufacturing domains like aerospace, automotive, energy, logistics, and other industries. This integration minimizes downtime and drives digital transformation, optimizing operations across various domains. In a smart factory, FPGAs handle high-speed data processing and precision control, while communication protocols keep machines synchronized. This combination delivers unmatched efficiency and flexibility in manufacturing.
This video has provided introduction to key electronic concepts from sensors and microprocessors to advanced tools like FPGAs and industrial communication. By mastering these skills, we are prepared to tackle challenges in modern electronics design and prototyping.